When you look up at the night sky and imagine the planets moving in the darkness, it can be calming to picture them as quiet, rounded worlds, turning slowly in space. Each planet spins, in its own time, in its own way. Some spin quickly, completing a day in only a few hours. Some spin slowly, so slowly that one sunrise can take longer than a year. Some lean gently as they turn. One seems almost to roll around the sun on its side. And all of them, in their different rhythms, carry a memory of how they were made. Tonight, we can rest with a simple question. Why do planets spin? It is a question that sounds small at first, almost like something a child might ask while looking through a window at the moon. But inside that question is the story of the whole solar system. It is the story of drifting gas and dust, of gravity pulling gently over long ages, of tiny grains joining together, of collisions, of balance, and of motion that continues because space is so quiet. There is no need to hurry through it. The planets themselves do not hurry in the way we do. They follow their paths, they turn, they keep time in patient circles. So we can begin slowly. A planet spins because long ago, the material that formed it was already moving. Before Earth was Earth, before Jupiter was Jupiter, before there were oceans, clouds, continents, rings, moons, or familiar sunsets, there was a large cloud of gas and dust. Astronomers call such a cloud a nebula. It was not still. Almost nothing in the universe is perfectly still. The cloud had tiny motions inside it, gentle currents, drifting regions, small twists, and slow rotations. Some parts moved one way, some parts moved another. But as gravity began to pull the cloud inward, those slight motions became more important. This is one of the key ideas. When something large and spread out shrinks inward, its rotation tends to become faster. A figure skater uses this same principle, though in a much smaller and more graceful way. When the skater spins with arms extended, the rotation is slower. When the arms are pulled inward, the spin becomes faster. The skater has not created new spin from nowhere. The spin was already there. It has simply been concentrated. The same idea applies to a forming solar system. A great cloud, wide and diffuse, begins to collapse under gravity. As it pulls inward, any small amount of rotation becomes more noticeable. The cloud flattens into a disk, with a young sun forming near the center. Around it, material continues to orbit. Dust grains bump into one another. Small pieces join, larger pieces form, and over time, planets begin to grow. The spin of each planet is connected to this beginning. It is connected to motion that existed before the planets had names, before they had surfaces, before they were worlds at all. There is a peacefulness in this idea. A planet's day is a memory. Each sunrise is related to motions that began in the ancient cloud from which the solar system formed. Earth turns today because the young Earth gathered matter that was moving and orbiting and colliding, and all of that motion had to go somewhere. It became, among other things, spin. Let us stay with that thought for a while. In physics, there is something called angular momentum. The name may sound technical, but the idea can be gentle. Angular momentum is the measure of how much rotation something has. It depends on how much matter there is, how that matter is spread out, and how fast it is turning. The important part is this. Angular momentum tends to be conserved. That means if nothing outside interferes very much, the total amount of turning motion stays the same. It may change form. It may move from one object to another. It may become a faster spin or a wider orbit, but it does not simply disappear. In space, where there is very little air or friction, motion can continue for a very long time. On Earth, when you spin a ball on the ground, it slows down. The ground rubs against it. The air pushes back. Energy is lost as heat and sound. But a planet in space does not have a floor beneath it. It is not rubbing against a table. There is no thick air surrounding the whole orbit to slow it quickly down. So once a planet is spinning, it tends to keep spinning. Not perfectly unchanged forever, but steadily, over immense spans of time. This is why Earth still turns. This is why Mars still turns. This is why Jupiter, with its broad bands of cloud, spins faster than any other planet in our solar system. A spinning planet is not being constantly pushed around by some hidden hand. It is continuing. It is carrying forward the rotation it inherited and gathered. This is often true in astronomy. Much of what we see is not motion beginning fresh every moment, but motion preserved. The moon orbits because it is falling around Earth, endlessly missing it. Earth orbits because it is falling around the sun, in a curved path shaped by gravity. And Earth spins because it formed from moving material, and space has allowed that spin to last. Now, slowly, we can imagine how a planet grows. At first, there are grains of dust, tiny pieces smaller than sand. They drift in the disk around the young sun. They collide gently, sometimes sticking together. Then clumps form. The clumps become pebbles, and the pebbles become larger bodies. Gravity becomes stronger as these bodies grow. They pull in more material. They are struck by other pieces. They merge, they shatter sometimes, and then gather again. This period of planet formation was not quiet in the way a finished planet is quiet. It was full of motion. But we can think of it softly, as a long process of gathering. Every small piece that joined a growing planet brought motion with it. If a pebble struck slightly to one side, it added a little twist. It could change the growing planet's spin a great deal. Over time, all of these impacts combined. Some canceled one another out. Some added together. The final spin of a planet depended on the total history of how it grew. This is why planets do not all spin at the same speed. They did not form in exactly the same way. They gathered different amounts of material. They experienced different collisions. They were shaped by different gravitational surroundings. The solar system has patterns, but it also has individual stories. Earth spins once every about 24 hours. Mars spins in a similar time, only a little longer than Earth. Jupiter spins in about 10 hours. Saturn also spins quickly. Venus spins very slowly, and in the opposite direction from most planets. Uranus spins on its side, with an extreme tilt. These differences are not random in the sense of meaningless, but they come from complex histories. Each planet carries the evidence of its own formation. Let us take Earth as a familiar example. Earth rotates from west to east. That is why, from our point of view, the sun appears to rise in the east and set in the west. But the sun is not truly traveling around Earth each day. It is Earth turning beneath the sunlight. One full rotation gives us one day. Not the day measured by clocks exactly, but the basic cycle of light and dark. Earth's spin gives rhythm to life. It brings morning and evening. It moves shadows across the ground. It helps shape winds and ocean currents. It gives the sky its slow daily motion. And yet this familiar turning began long before there was anything here to measure it. Long before there were birds to sing at dawn, or people to watch the sunset, the young Earth was already spinning. Its early spin was likely different from today's. It may have been faster. The length of an Earth day has changed over time. The moon has played a quiet and important role in that change. The moon's gravity pulls on Earth. It raises tides in the oceans, and also in the solid body of Earth, though those solid tides are much smaller. Because Earth spins faster than the moon orbits, the tidal bulges are carried slightly ahead of the line between Earth and moon. This creates a gravitational interaction. It slowly transfers some of Earth's rotational energy to the moon's orbit. As a result, Earth's rotation gradually slows, and the moon slowly moves away. Not quickly, only a few centimeters each year, a very small amount, almost nothing in a human lifetime, but important over hundreds of millions and billions of years. Long ago, Earth's days were shorter, perhaps only 5 or 6 hours in the very early history of the planet, depending on the time and the model. Later, still far in the past, days may have been 22 hours, or 21, gradually lengthening. The present 24-hour day is not fixed forever. It is a moment in a long, slow process. There is something restful in knowing that even days are not absolute. They are part of a slow conversation between Earth and Moon, a conversation of tides, gravity, spin, and orbit. The Moon also may have begun in a great collision. The leading idea is that a Mars-sized body struck the early Earth at an angle. This impact sent material into orbit around Earth. That material later gathered to form the Moon. Such a collision would have strongly influenced Earth's spin and tilt. So the day we know and the Moon we see may both trace back to a single early event, a deep moment in the planet's formation. Again, rotation is memory. The planet turns because of what happened to it. The Moon circles because of what happened to it. The system we see now is the softened result of ancient motion. Now gently we can move outward to the giant planets. Jupiter is the largest planet in the solar system. It contains more mass than all the other planets combined, and it spins very fast. A day on Jupiter is only about 10 hours long. Because Jupiter is so large, and because it spins so quickly, it is not a perfect sphere. It bulges at the equator. This happens because rotating material experiences an outward effect at the equator. The faster the rotation, the more noticeable the bulge. Saturn also has a strong equatorial bulge. Its rapid spin and lower density make it visibly flattened. When we look at images of Saturn, we see a wide, pale world, gently banded and circled by rings. But it is also rotating rapidly, turning beneath those rings in a little more than 10 hours. The gas giants likely spin quickly because they gathered large amounts of material from the solar nebula. As gas fell inward onto these growing worlds, it brought angular momentum. The planets became massive, and their rotation became rapid. For giant planets, there is no solid surface in the familiar sense, so measuring a day can be more complicated. Clouds can move at different speeds at different latitudes. Magnetic fields and radio emissions can give clues to the rotation of the deeper interior. Even a simple question like, "How long is a day on Saturn?" can have a quiet complexity. The universe often works that way. The childlike question opens into layers. Why do planets spin? Because of angular momentum, because of formation, because of collisions, because of conservation, because space is almost frictionless, because each world has kept a part of its beginning. And with each answer, there is another softer detail beneath it. Now consider Venus. Venus is close to Earth in size, sometimes called Earth's sister planet, though the two are very different worlds. Venus is covered in thick clouds. Its surface is extremely hot. Its atmosphere is dense, and its rotation is unusual. Venus spins very slowly. It takes about 243 Earth days to rotate once relative to the distant stars. That is longer than its year, which is about 225 Earth days. Even more strangely, Venus spins in the opposite direction from most planets. This is called retrograde rotation. If you could stand on Venus, beneath the thick atmosphere, the sun would rise in the west and set in the east, though very slowly, and the clouds would hide it. Why does Venus spin this way? The answer is not completely settled. There are several ideas. One possibility is that Venus was struck by a large object early in its history, changing its rotation. Another is that gravitational interactions with the sun, combined with atmospheric tides in its dense atmosphere, gradually altered its spin. The sun's gravity can create tidal effects, and Venus's thick atmosphere can respond to heating in complex ways. Over long times, these effects may have slowed and even reversed the planet's rotation. There may not be a single simple cause. Venus reminds us that planets can change. Their spins are inherited, but they can be modified. Gravity can tug, tides can slow, collisions can alter, atmospheres can matter, The story of rotation is not only how motion begins, but also how it is reshaped. Now, we can drift to Uranus. Uranus is a pale blue-green planet, far from the Sun. It has a striking feature. Its axis is tilted by about 98 degrees. In simple terms, it rotates almost on its side. Most planets have axes that are somewhat upright compared to their orbits, though they may lean. Earth leans by about 23.5 degrees. That tilt gives us seasons. Mars has a similar tilt. Jupiter has only a small tilt. But Uranus is tipped far over. As it moves around the Sun, one pole can face the Sun for many years, while the other is turned toward darkness. Then, half an orbit later, the situation reverses. A year on Uranus lasts 84 Earth years, so its seasons are long and unusual. Why is Uranus tilted so much? Again, a likely explanation involves impacts during formation. A large collision, or perhaps several significant collisions, may have knocked the young planet onto its side. Another possibility involves gravitational interactions with other bodies or a massive satellite system long ago. The exact history is not certain, but the extreme tilt tells us that Uranus had a different past from its neighbors. It is not only spinning, it is spinning in a way that remembers something unusual. A tilt is also a kind of history. Every planet has an axis, an imaginary line around which it turns. The angle of that axis matters. It determines how sunlight spreads across the planet over time. It affects climate. It creates or softens seasons. It changes the length and character of days at different latitudes. On Earth, our tilt means that the northern and southern hemispheres take turns leaning toward the Sun. Summer comes when a hemisphere receives more direct sunlight and longer days. Winter comes when it receives less direct sunlight and shorter days. This, too, comes from planetary spin, but the angle at which it turns. So when we ask why planets spin, we are also asking why planets have days, and why many have seasons, and why the sky seems to move. Spin is woven into the experience of a world. It is a simple motion with many consequences. Let us return now to the beginning, because repetition can be restful, and the beginning is important. The solar system formed from a rotating cloud. The cloud collapsed. As it contracted, its rotation became more pronounced. A disk formed around the young sun. Inside that disk, matter orbited. Dust became pebbles. Pebbles became planetesimals. Planetesimals became protoplanets. Protoplanets became planets. At each stage, motion was carried forward. At each collision, spin could be added, subtracted, redirected, or intensified. And when the planets were formed, they kept turning because there was little to stop them. This is the heart of the answer. Planets spin because motion is conserved. They spin because they were born from moving material. They spin because space allows rotation to endure. The same principle appears everywhere. Stars spin, moons spin, asteroids tumble, galaxies rotate, accretion disks whirl around young stars and black holes. Rotation is one of the common languages of the universe. Gravity pulls matter together, and angular momentum shapes how that matter moves as it gathers. If everything could fall straight inward, perhaps the story would be simpler. But because matter has sideways motion, it orbits, spirals, flattens into disks, and spins. This is why planets do not just fall directly into the sun during formation. They have orbital angular momentum. They move sideways as gravity pulls inward. The result is orbit. And on smaller scales, as matter gathers into planets, some of that turning motion becomes planetary rotation. It is useful to separate two motions that are often confused. A planet revolves around the sun. That is its orbit. A planet rotates on its axis. That is its spin. Earth revolves around the sun once each year. Earth rotates once each day. Both motions come from the early solar system. Both are governed by gravity and angular momentum. But they are not the same. The year is the time it takes Earth to complete one orbit. The day is the time it takes Earth to turn once. Other planets have other combinations. Mercury orbits the Sun in only 88 Earth days, but rotates slowly. Its spin and orbit are locked in a special pattern called a spin-orbit resonance. Mercury rotates 3 times for every 2 orbits around the Sun. This means its solar day, from one sunrise to the next, is much longer than its year. The Sun's strong gravity has shaped Mercury's rotation over time. Here again, we see that spin can be changed by tides. Close to a massive body, tidal forces can be strong. They can slow rotation, adjust it, and sometimes lock it. Our moon is tidally locked to Earth. It rotates once in the same time it orbits Earth once. That is why we always see nearly the same face of the moon. The moon does spin, but its spin is synchronized with its orbit. This can seem surprising. Because the same side always faces us, the moon may appear not to rotate. But if it did not rotate at all, we would see all sides over the course of its orbit. Instead, it turns once as it goes around, keeping one hemisphere directed toward Earth. Many moons in the solar system are tidally locked to their planets. Over time, gravity has slowed their spins into this stable rhythm. Planets can also become tidally locked to stars, especially if they orbit very close. Many exoplanets, planets around other stars, may keep one side facing their star and one side facing away. On such a world, there may be no ordinary day and night cycle. One hemisphere may be in constant light, the other in constant darkness. Between them may be a band of twilight. But even there, rotation exists in relation to orbit. Spin is not absent. It has simply become synchronized. Tidal locking is one of the ways the universe turns motion into rhythm. A fast spin slows. A mismatch settles. Over time, gravity tends to smooth certain differences. But it does not erase motion. It rearranges it. Now, gently, we can think about what would happen if a planet did not spin. Imagine a world with no rotation at all, orbiting its star but not turning relative to the distant background. Its day and night pattern would be very different from Earth's. Depending on its orbit, each region might experience long periods of sunlight and darkness. Atmosphere and oceans, if present, would move in different ways. Weather patterns would not resemble those we know. On Earth, rotation contributes to the Coriolis effect. This effect influences the direction of winds and ocean currents. It helps shape cyclones and trade winds. It organizes large-scale circulation. Because Earth spins, moving air does not travel in a simple straight path over the rotating surface. It curves, relative to the ground. In the northern hemisphere, moving air tends to deflect to the right. In the southern hemisphere, to the left. This matters for weather, climate, and ocean flow. So planetary spin is not just a clock, it is a sculptor of atmospheres. On Jupiter and Saturn, rapid rotation helps produce long bands and powerful jet streams. On Earth, rotation helps distribute heat. On Mars, rotation shapes winds and dust movement. The turning of a planet affects how it feels, how it breathes, how clouds move above it, and yet the cause remains simple at the root. Ancient motion, conserved and carried onward. There is comfort in how many things come back to that. A planet spins because it formed from things that were already moving. It keeps spinning because there is little friction in space. It may spin faster or slower because of collisions, tides, and internal changes. It may lean because of impacts or gravitational interactions. It may become locked because of tidal forces. But in every case, the spin has a history. Now, let us consider another quiet detail. A planet's spin can change if its mass shifts. This happens because angular momentum depends not only on speed, but on how matter is distributed. On Earth, changes in the distribution of mass can slightly affect the rotation. Large earthquakes, melting ice, movement of water, and circulation in the atmosphere can all cause very tiny variations in the length of the day. These changes are extremely small, fractions of a millisecond, but they are measurable. Earth is not a rigid, unchanging ball. It has a molten outer core, a mantle that slowly flows over geologic time, oceans that move, air that circulates, ice that grows and melts. All of these can affect rotation in slight ways. Even the planet's axis can wobble. There is a motion called precession, where Earth's axis slowly traces a circle over about 26,000 years. This is caused mainly by gravitational tugs from the Moon and Sun on Earth's equatorial bulge. Because Earth is slightly flattened and bulging at the equator, external gravity can pull on that bulge and create a slow wobble. There are also smaller wobbles, such as nutation, and shifts in the position of the poles. These motions are gentle and slow. They remind us that spin is not just a single number. It is a living balance, shaped by the planet's body and its relationships. A spinning planet is not perfectly still except for rotation. It flexes, it responds, it wobbles, it exchanges energy, it interacts with moons, with the sun, with its own moving layers. But from the human point of view, Earth's rotation feels steady. The sun rises, the sun sets, the stars cross the sky. The day returns. This steadiness helps us rest. It gives us a rhythm, and that rhythm is part of a cosmic pattern. All around the solar system, worlds are turning. Mercury turns slowly in its resonance. Venus turns very slowly backward. Earth turns with its familiar day. Mars turns with a day just a little longer than ours. Jupiter turns swiftly. Saturn turns swiftly. Uranus turns on its side. Neptune turns in about 16 hours. Each planet is different, but each is part of the same family of motions. There is no need for them to be identical. Nature rarely repeats in exact copies. Instead, it creates variations. The principle is shared, while the details differ. Now, if we imagine the early solar system again, we can see why perfect stillness was never likely. A cloud in space may appear calm from far away, but within it, particles are moving. Gas as temperature, and temperature means motion. Turbulence stirs regions of the cloud. Nearby stars may send waves through it. Gravity gathers certain areas more strongly. No part is perfectly balanced. When collapse begins, small differences become large. A slight rotation becomes a disk. A small sideways motion becomes an orbit. Then, within the disk, collisions are not all head-on. Most happen at angles. An off-center impact naturally creates spin. If you push a door at the hinge, it does not swing much. If you push near the edge, it rotates. In the same way, when material strikes a growing planet away from its center, it can add rotation. Many impacts over time build a final spin. Some planets may have experienced one especially important impact. Others may have received many smaller contributions. The final result is a sum, a long addition problem written in dust, rock, ice, gas, and gravity. And after the addition is complete, the planet turns. It does not need fuel to keep turning in the usual sense. It is not like a machine that must be powered. It is more like a drifting object that continues moving until something changes it. In physics, motion persists unless acted upon. Rotation persists too. This idea was made clear in the laws of motion. An object in motion remains in motion unless a force changes it. For spin, a rotating body remains rotating unless a torque changes it. A torque is a twisting influence. Tides can create torques. Collisions can create torques. Gravitational pulls on bulges can create torques. Friction inside a planet can redistribute spin. But without a strong torque, spin continues. The quietness of space helps preserve it. There is no wind blowing against the planet as a whole. No cosmic ground to scrape against. Only delicate interactions, acting slowly. So the planets spin and spin and spin. Not hurriedly, not with effort, just continuously. Now we might wonder why most planets in our solar system spin in the same general direction as they orbit. This is because they formed from the same rotating disk. The disk had a dominant direction of motion. Most material orbited the young sun in that direction. The sun itself rotates in that general direction. Most planets orbit in that direction. Most planets also rotate in that direction, though the match is not perfect. Venus and Uranus are exceptions in different ways. This shared direction is evidence of common origin. It is like seeing leaves floating in a slow whirlpool. Most follow the same swirl because the water itself is moving. The planets are not leaves, of course, and the solar nebula was not water. But the image can help. A rotating disk gives a preferred direction. The planets inherit it, unless later events alter them. The same is true in many young star systems. Astronomers observe disks around young stars. These protoplanetary disks are places where planets may be forming. They glow in infrared light and radio wavelengths. They can show gaps where planets may be clearing paths. They are wide, flat, rotating structures. In them we see the early conditions that likely gave rise to our own solar system. We are not only guessing from theory, we are watching similar processes elsewhere. Across the galaxy, young stars are surrounded by disks. Dust is gathering. Some of it may become planets. Some of those planets, some will spin quickly, some slowly, some tilted, some locked. Each will carry the motion of its birthplace. In this way, Earth is not alone. Our day is one example of a broader cosmic habit. Matter gathers, and because it was moving, it turns. Now, slowly, let us think about the sun. The sun also spins. It formed from the same collapsing cloud. But because the sun is made of hot plasma, not solid rock, different parts rotate at different rates. The equator rotates faster than the poles. This is called differential rotation. Gas giants also show differential motion in their atmospheres. Even Earth's atmosphere and oceans move differently from the solid ground. Rotation in fluid bodies is often layered and complex, but the origin is again connected to the forming cloud. The sun took most of the mass of the solar system. The planets took only a small fraction. Yet the planets hold a large share of the solar system's angular momentum in their orbits. This is an interesting detail. The distribution of angular momentum in a forming system is complex. Magnetic fields, solar wind, disk interactions, and outflows can move angular momentum around. The young sun may have lost some angular momentum through interactions with its magnetic field and the surrounding disk. In star formation, getting rid of excess angular momentum is important. If a collapsing cloud conserved all of its rotation in the central star, the star could spin too fast. So disks, jets, magnetic fields, and planets all play roles in redistributing motion. The universe is patient with these balances. It does not need to solve them quickly. Over thousands, millions, and billions of years, gravity and motion arrange matter into stable patterns. The result for us is a solar system where the sun turns, planets orbit, planets spin, moons orbit, and many moons spin in step with their orbits. Layer upon layer of turning. Circles within circles. Not perfect circles, and not perfect repetition, but steady enough to guide clocks and calendars. A day, a month, a year. All of these are motions. All of them are rooted in spin and orbit. Now, if we return to Earth again, we can feel the meaning of rotation more personally. As Earth turns, different places pass into sunlight. Morning moves across the planet, not as a thing by itself, but as a boundary between shadow and light. This boundary is called the terminator. It sweeps across oceans, mountains, forests, and cities. At any moment, somewhere on Earth, dawn is arriving. Somewhere else, sunset is softening the sky. Elsewhere, midnight is deep and quiet. All of this happens because Earth rotates. The planet turns, and we experience time. We divide that turning into hours, minutes, and seconds. Our clocks are more precise now, based on atomic vibrations, but the original human sense of a day comes from the rotation of Earth. The spin of a planet becomes the rhythm of sleep and waking. Plants open and close. Animals rest and move. Human bodies follow circadian rhythms, internal cycles tied to light and dark. So the ancient spin of Earth, reaches into biology. It reaches into the way leaves move, the way birds migrate, the way people feel sleepy at night. Something that began as angular momentum in a forming solar system now helps shape the quiet feeling of evening. This can be a comforting connection. The planet turns, and we let go of the day. The same rotation that brings morning also brings night. There is nothing sudden about it from the planet's point of view. Only a steady turning. A gradual movement into shadow, a gradual return to light. Now let us settle once more into the physics, softly. Why do planets spin? Because in the early solar system, there was angular momentum. As gas and dust gathered, that angular momentum had to be conserved. Some became orbital motion. Some became spin. Off-center collisions added rotation. Accreting material carried motion. Later, tides and impacts changed the details. And in the near vacuum of space, rotation can last for billions of years. That is the simple answer. But it is also a layered answer. The spin rate of a planet depends on where it formed, how it grew, what struck it, whether it has moons, how close it is to the sun, whether it has a thick atmosphere, whether its interior can dissipate energy, and how its mass is arranged. A planet is a physical object, but also a history. You cannot fully explain its rotation without telling part of its life story. For Earth, the story includes the solar nebula, accretion, a likely giant impact, the formation of the moon, tidal slowing, internal motion, and tiny ongoing changes. For Venus, the story may include solar tides, atmospheric tides, and perhaps impacts. For Uranus, the story likely includes a great tilting event. For Jupiter and Saturn, the story includes rapid growth and the gathering of gas with angular momentum. For Mercury, the story includes tidal interaction with the Sun and resonance. Each world answers the question in its own quiet way. And yet, beneath all the details, the same principle remains. Motion continues. Turning is conserved, unless something twists it. Space is wide, and friction is small. So planets keep their ancient spin. Now we can imagine a small rock in space, an asteroid. Many asteroids spin too. Some rotate in hours, some tumble irregularly. Some are shaped like potatoes, or rubble piles loosely held by gravity. Their spins can be changed by impacts, by sunlight, and by the uneven emission of heat. There is an effect called the Yorp effect, where sunlight can gradually change the spin of small bodies. A small asteroid absorbs sunlight, and later radiates heat. If its shape is uneven, the escaping heat can create a tiny torque. Over long periods, this can speed up or slow down rotation. For planets, this effect is generally too small to dominate, but for small asteroids, it can matter. This reminds us that the universe has many gentle forces. Not all change comes from large collisions. Some changes come from tiny effects repeated over long times. A faint push, a slight imbalance, a gradual slowing, a patient adjustment. The same is true of tides. A tide raised by gravity may seem small, but over millions of years, it changes worlds. The moon is moving away from Earth. Earth's day is lengthening. The moon's own rotation has been locked. These are not sudden changes. They are slow enough to feel almost eternal, but they are real. A sleepy mind can rest in slow processes. They do not demand attention all at once. They simply unfold. Now another thought. If planets spin because of angular momentum, why are they round? This is a related but separate idea. Planets are round because gravity pulls matter inward from all directions. When an object is large enough, its own gravity overcomes the strength of rock or ice, and it settles into a roughly spherical shape. Spin modifies that sphere, making a planet bulge at the equator. So a spinning planet is usually not a perfect sphere, but an oblate spheroid, slightly wider around the middle. Earth is like this. The equatorial diameter is larger than the polar diameter by about 43 kilometers. Compared with the size of Earth, this is small, but measurable. Jupiter and Saturn are more noticeably flattened. Their rapid rotation and fluid nature make the effects stronger. So spin shapes a planet's form. Gravity makes it round. Rotation makes it slightly broad. These two influences, gravity inward and rotation outward at the equator, find a balance. Again, motion and gravity working together. Again, a quiet compromise. Now we can think about exoplanets, distant planets around other stars. Thousands have been discovered. Many are very close to their stars. Some orbit in only a few days. Because they are close, tidal forces are strong. Many of them are likely tidally locked. Their spins may have slowed until one side faces the star continuously. Other exoplanets are far out, or giant, or young, and may spin rapidly. Astronomers are beginning to measure rotation in some of these distant worlds, sometimes by observing changes in brightness, or broadening in spectral lines, or patterns in atmospheres. The details are difficult because exoplanets are so far away, but the same physics applies. They formed in disks. They gathered moving material. They were shaped by collisions, tides, and gravity. They spin because they have histories of motion. It is soothing to imagine that across the galaxy, countless planets are turning. Some around red dwarf stars, some around sun-like stars, some young and hot, some old and cold, some rocky, some gaseous, some with moons, some alone. On all of them, if they rotate, there is some kind of day, or some relationship between spin and light. Even if no one is there to watch, the planet turns. Even if no names are given, the motion continues. Now, as we move toward rest, we can let the main ideas become simple again. The universe began this story with motion. A cloud of gas and dust was not perfectly still. Gravity pulled it inward. As it contracted, rotation became more organized. A disk formed. The sun grew at the center. Planets formed in the disk. They gathered material that was already moving. Collisions added and changed spin. Conservation of angular momentum kept the motion from vanishing. Space offered little resistance, and so the planets kept turning. That is why planets spin. Not because they are being wound up each day, not because they need to push against something, not because the sun drags them around like wheels. They spin because they were born from motion, and motion endures. This is one of the most peaceful ideas in physics. Things continue unless changed. A planet in rotation remains in rotation, slowly adjusted by the gentle hands of gravity, tides, and time. Earth is one of these planets. It turns beneath us now. Even when we are still, Earth is rotating. At the equator, the surface moves eastward at about 1,670 kilometers per hour. We do not feel this speed because everything around us is moving with Earth, and because the motion is steady. The air, the ground, the oceans, and we ourselves share the rotation. There is no sudden acceleration to notice, only steadiness, only the familiar cycle of sky and light. The stars appear to rise and set because Earth turns. The moon crosses the sky because Earth turns, and because the moon orbits. The sun seems to travel from morning to evening because Earth turns. Much of the sky's daily motion is our own motion, carried quietly by the planet. This can be a soft thought at bedtime. You do not need to move. The Earth is already moving. You do not need to keep time. The planet is keeping time. You do not need to hold the day in place. The turning will carry it onward. Night comes because Earth rotates away from the sun. Morning comes because Earth rotates back. The cycle is larger than us, older than us, and steady enough to trust. Now the question, why planets spin, has become less like a puzzle and more like a lullaby of physics. They spin because the solar system formed from a rotating cloud. They spin because angular momentum is conserved. They spin because collisions and accretion gave them turning motion. They spin because space does not easily slow them. They spin in different ways because their histories differ. Earth spins with a day we know. Mars spins with a similar rhythm. Jupiter and Saturn spin quickly. Venus spins slowly backward. Uranus spins tilted on its side. Mercury spins in resonance with its orbit. The moon spins once per orbit, keeping its familiar face turned toward Earth. Every rotation is a record. Every day is a trace of formation. Every tilt is a clue. We can let that be enough. Some details remain uncertain, even for scientists. Venus still holds questions. Uranus still holds questions. The exact early spin of Earth still depends on models. But uncertainty does not disturb the main calm. The broad answer is steady. Planets spin because they inherited motion, and they keep it. The solar system is a place of conserved motion, gently altered over time. And now as this thought settles, imagine Earth as a blue and white sphere in space. Clouds drift above oceans. Continents pass through sunlight. The line of evening moves slowly across the surface. Cities grow dim under the coming night. Forests darken. Deserts cool. Waves continue their quiet motion. The atmosphere turns with the planet. The moon, farther away, keeps its slow orbit. The sun shines steadily from the center of the system. And Earth turns. It turns without effort. It turns because it has always been turning, in one form or another, since its earliest days. It turns because matter once gathered, and the gathered motion remained. It turns through night. It turns through morning. It turns through seasons. It turns through ages. The other planets turn too, each in its own rhythm. A slow Venus day, a swift Jupiter day, a tilted Uranus season, a cold Neptune rotation, a red Martian sunset. All moving quietly in the dark, all shaped by the same gentle laws. Gravity gathers, motion continues, time passes, worlds spin. And here on this rotating Earth, it is enough to rest. The planet is steady beneath you. The night is part of its turning. The stars seem to drift because Earth is carrying you with it. There is nothing to do but let the motion continue. Let the thought become simple. Planets spin because they were born from motion. They keep spinning because space is quiet. And Earth, our home, turns softly onward, carrying the night with it, carrying you with it, toward morning, in its slow and ancient rhythm.